Welcome back, everybody. In this portion of today's lesson, I'm going to be talking about how we can actually work out the common ratio of a geometric sequence, as well as the nth term for a geometric sequence. After that, we're going to look at an example where we can actually make some calculations using the nth term of a geometric sequence. Let's have a look at how we work out the common ratio. So we have just discussed that the main feature of a geometric sequence is the fact that there is a constant or common ratio. So we discussed that that is an actual number that each term is multiplied by in order to get to the next term. So if I give you the pattern 2, 4, 8, 16 going on, I can see that each term has been multiplied by 2 to get to the next term. So that, in fact, is the common ratio. So if I want to actually calculate the value of the common ratio, because sometimes in an example, it might not be so obvious. For this example, we can kind of see immediately that 2 has been multiplied by 4, and 4 has been multiplied by 2, 8 has been multiplied by 2 going on. So we want to see if there's actually a concrete way that I can calculate the common ratio. The common way that I write down the common ratio is term 2 over term 1. So just a reminder, this is the value of term 2 over the value of term 1. For this pattern, we can see that the value of term 2 was 4, and the value of term 1 is 2. And 4 over 2 is positive 2. So we can see that the common ratio is 2. I can also confirm my common ratio by saying term 3 over term 2. The value of term 3 for this pattern is 8. Then I'm going to divide that by the value of term 2, which is 4. And that gives me a common ratio of 2 again. So I'm hoping that everyone can see that we can calculate the common, sorry, this says common difference, guys. It's supposed to be common ratio. We can define the common ratio to be the term value over the term value that comes before it. So over here, we did term 2 divided by term 1. Then we did term 3 divided by term 2. It's always going to be the term value over the term that comes before it. So Tn over Tn minus 1. The next thing that we are going to do, everyone, is we are going to find a way to actually generate the nth term for a geometric sequence. We know that in a pattern, we often call the first term A. So in this case, T1 would be equal to A. So I'm going to write that down. So we're going to have T1 is equal to A. And we know that each term of a geometric sequence is multiplied by the common ratio to get to the next term. So term 2 will be AR, because it's going to be the first term multiplied by R. Then to get the third term, I'm going to take the value of the second term, but I have to multiply it by R again. So T3 will be equal to AR squared. Term 4 will be the value of term 3, which we saw is AR squared. But again, I have to multiply by the common ratio to get to the next term. So I'm going to multiply by R again, which means the term 4 would be equal to AR cubed. I'm just going to swap my color, so hopefully it's a bit easier on your eyes, guys. The value of term 4 is AR cubed. And in order to get term 5, I have to multiply it again by the common ratio. So term 5 would be AR to the power of 4. So we can see that each time I am multiplying the term that comes before the present term by the common ratio, because we know that the common ratio is the main characteristic of a geometric sequence. So we can therefore say that the nth term for a geometric sequence can be written as Tn is equal to A times r to the power of n minus 1. Now you might be asking, why the n minus 1? If I go back to my previous slide, I can see that each time the power of r was 1 less than the term value. So here we can say that there was r to the power of 0, because we know that that has a value of 1, because anything to the power of 0 has a value of 1, so that means that r was to the power of 0. Here, r was to the power of 1, which makes sense because this is 1 less than the term value. For term 3, r was squared, and that is 1 less than the term value. For T4, we had r cubed, which is 1 less than the term value. So every single time we're finding the term value in a geometric sequence, the ratio is to the power of the term number minus 1. So if I wanted to write down T43, I'm going to have A r to the power of 42, because 42 is 1 less than the term number. I'm hoping that you're all with me. Please just take a second to take it all in. If I wanted to write term 100 in terms of A and R for a geometric sequence, T100 would be equal to AR to the power of 99. Why 99? Because 99 is 1 less than the actual term number. So please keep that in mind as we move on to our next few examples. Let's have a look at the next slide. Great, everybody. Let's have a look at this example. So we have been asked to consider the sequence an eighth, a quarter, a half, 1, going on to 128. Please note that if there's a full stop after a term of the pattern, that means that this is the last term of the pattern. So the first term is an eighth, and the last term of this pattern is 128. Let's have a look at the questions. So A has asked me to write down the fifth term of the sequence. B is asking me to determine a formula for the nth term of the sequence. C is asking me to determine the value of the seventh term. And then last but not least, I've been asked how many terms are there actually in the sequence. So I know that this is the value of the last term, but I want to know what is the position number of that term. Let's get going with A. Great, guys. So let's start with A. A is asking us to write down the fifth term of the sequence. So we're going to be thinking about certain strategies with patterns in order to see what type of pattern this is. If we're looking between the terms of an eighth, a quarter, a half, 1, I'm sure that everyone will agree with me that there isn't a common difference. And a common difference is the main property of an arithmetic sequence. Cool. I hope that everyone's still with me. We are going to be looking to see if there is a common ratio between the terms of the sequence. If there is a common ratio, then we can use the rules of a geometric sequence to continue asking or answering these questions. Let's go back to the board. So we have the common ratio, which we discussed earlier, is equal to term 2 over term 1, which will be equal to a quarter over an eighth. And a quarter over an eighth gives me an answer of 2. I can also check my common ratio by doing term 3 over term 2, which is 1/2 over a quarter, which will give me a common ratio of 2. So that means that between each term of this pattern, we have multiplied by 2. So in order to determine the value of term 5, I'm going to multiply by 2. So that means that the value of the 5th term of the sequence is in fact 2. Great, guys, let's move on to B. So we need to now determine a formula for the nth term of the sequence. We can see that A is an 8th just because that is the first term in a sequence. And my common ratio, which I found in A, is 2. For finding the nth term, we know that Tn is equal to A r to the power of n minus 1. So the nth term for the sequence will be Tn is equal to an 8th times 2 to the power of n minus 1. So that is my nth term for the sequence. Let's move on to C, everybody. We are doing well. Thank you for staying with me. I hope this is making sense. We now need to determine the value of the 7th term. Cool. I hope that everyone's with me that the value of the 7th term means that the term number for this example is 7. So n is 7. So what I have to do is substitute n is equal to 7 into Tn. This is going to allow me to find the actual value of the 7th term. Let's do the calculation together. So I'm substituting in 7 for n. So I'm going to have an 8th times 2 to the power of n minus 1. But please remember, I am substituting in n with 7. So I'm going to have that T7 is going to be equal to an 8th times 2 to the power of 6. Let us pop that into our calculator. So I've got 1 over 8 times 2 to the power of 6. So that means that term 7, whoopsie, sorry guys, term 7 is equal to 8. Great. D, I've been asked how many terms are in the sequence. That means that I'm looking for the n that matches the Tn of 128 because I know that is the last term of the sequence. So I'm going to have 128 is equal to an 8th times 2 to the power of n minus 1. I'm looking to solve for n. So the first thing I'm going to do, everybody, is to try and isolate the n. So I'm first going to say 128 divided by an 8th. Sorry, the fraction doesn't want to work for me, everybody. There we go. 1 over 8, which is going to give me 1,024. So my next line can be written as 1,024 is equal to 2 to the power of n minus 1. I'm going to ask you all to use your calculators to find the prime factors of 1,024, and I'm hoping that everyone will get 2 to the power of 10. So now if I'm solving this exponential equation, I can drop my bases, which means that 10 will be equal to n minus 1. If I move this negative 1 over, I'm going to have 11 is equal to n, which means that there are 11 terms in this sequence. Great, so now that we've looked at the introduction to geometric sequences, after the break we're going to look at more strategies for geometric sequences. See you soon.